Okay, lecture 2 and Calc 4, lecture 2, it's Gaussian elimination. The first thing we should know is, well, first of all, a matrix. I guess everybody knows what a matrix is from, say, college algebra. Now, a reduced row echelon form for a matrix, which is abbreviated as RREF. You might have seen RREF on your calculators. So an RREF form, in fact, that's form. That form is has these properties. So when I go through them, I will show you on that example over there. First is a row that doesn't contain entirely of zeros. If a row doesn't contain entirely of zeros, then the first entry in that row is a 1. This row here contains entirely of zeros. This one does not. And the first entry here is 1. This one does not. The first entry is 1, and this one is also 1. And when you do this, usually the first row contains a 1 at this position. Second, now this one we call a 0 row. So this is a 0 row, and definitely this is a non-zero row. So the second property is that the 0 rows come at the end, like this. So they are grouped at the bottom of the matrix. The third one is if I have two non-zero rows, the one which is above the other one, or let's say the one which is below the other one, the leading one in this row is further to the right. So this is to the right of this. This is to the right of this. This is to the right of this. And vice versa. This is to the left of this. And at the end, each column that has a leading one has nothing else. Okay? So everything else in that column is 0. So this form is called a reduced row echelon form, and our goal is, given a matrix, to reduce it to this. So let me give you an example. In fact, let me erase all these things. I guess you have some idea what it is. By just looking at this example, you can tell. Okay, so let me give an example here. First of all, matrices in reduced row echelon form. Let me give you an example. That was one example, 0, 0, 0, 2, 5, say, 0, 1, 0, 0, say, 8, for example, and then this one can be 1 here, 1, 5, 25, something like that. So the leading ones are here, here, and here. So this can happen both anyway. Well, this is RRF. This is an RRF form. So now let's see. Well, I can. Well, there might be numbers here, so it doesn't have to be 0, but it can be numbers here. So 1, 0, 0, 0, 1, 0, 0, 0, 0. And well, let's have one which is not R. Let's put it on somewhere. Okay. Okay, so let me start with an example and then I just write an example on the fly. So I didn't prepare anything. So let's say I have let's say x1 plus 2x2 minus 3x oh, my 3 minus x3 say plus 2x4 minus 3x5. Let's write 0 on the other side, so we don't have to do too much here, and we have 2x1 minus 3x2 plus x3 minus x4 plus say 2x5 is 0, and the last one will be like 3x1 plus x2, or let me say 3x1 minus x2 minus x2 and x3 plus x4 minus x5 is 0. So there is no x3 here, which means that it's like 0 times x3. Let me put this in matrix form. So the coefficient matrix A is this 1, 2, and negative 1, and 2, negative 3, 1, and 2, minus 3, 1, negative 1, and 2, and the last one is 3, negative 1, 0 here, and 1, negative 1. Okay. So we have to use the reduction that we did. So this and this should be 0, then this should be 0, and then we go up. If that is the case. So let me get rid of these two first. So minus 2 times row number 1 plus row number 2, and that goes into row number 2. And then we write the other operation. Let's do them together. Row number 1 plus row number 3, and that goes to row number 3. Okay, if I do this, let me do the operations here. So minus 2 times this is minus 2, and minus 4, and 2, and minus 4, and 6, right? Minus 4, 2, minus 4, and 6. So I have 2 here, minus 3 here, 1, negative 1, and 2. Let's put together. Is 0, minus 7, and that is 3, and minus 5, and that is 8. So this gives me 1, 2, negative 1, 2, negative 3. Well, let's just do it here. So let's change this. So the second one will become 0, minus 7, and 3, minus 5, and 8. Now, minus 3 times row 1 is minus 3, minus 6, plus 3, minus 6, plus 9. Right? So that is minus 3, minus 6, 3 plus, that's minus, that plus 2. And 3, negative 1, 0, 1, So that is 0, minus 7, and 3, and minus 5, and 8. So the third row will be 0, minus 7, and 3, minus 5, and okay. Now I will use this to eliminate this. So let's say minus row 2 plus row 3 goes to row 3. Well, you can see that minus this is plus 7, minus 3, plus 5, minus 8. Then you add, you will get 0. So this will give me all zeros here. Okay. Next, I will divide this second row by negative 7. So minus 1 over 7 times row 2 goes to row 2. Okay, so this will be 1 here. That is minus 3 over 7, right? Minus 3 over 7. That is plus 5 over 7, minus 8 over 7. Okay, so now I have a leading 1 here, another leading 1 here. This column is okay, this is 0, this is 0. This column is not okay, this should be 0. So I have to do something, so I will get rid of this 2 here. So minus 2 times this plus this will give me 0 here. So I will do that. The next operation will be minus 2 times row number 2 plus row number 1. And this goes to row number 1. Oh, row number 1, let me see, let me write that here. I have 1, 2, negative 1, 2, negative 3, and I have 0, minus 2, and the minus 2 times this is 6 over 7, minus 2 times this is minus 10 over 7, and that is 16 over 7, right? So minus 2, that's 6, that's minus 10, and that's 16. So I will get 1, 0, and that is minus 1 over 7, I guess, and this will be 14, that is 4 over 7, and that's 21, minus 21, 16, that is minus 5 over 7. So, okay, let me double check. So that's 0, 6 over 7 minus 1, that's 6 minus 7, that's minus 1. 2 minus 10 over 7, that's 14 minus 10, that's 4. And 3 times 7 is 21, 21 minus 16, that is 5. So let's get rid of this. And I have 1, 0, negative 1 seventh, 4 over 7, and minus 5 over 7. So, this is now in reduced row echelon form. Let's double check. First of all, what I would check is the 0 rows, 0 row, there is just one 0 row which is at the bottom of this. Then I have leading 1s. Each row which is not 0 has a leading 1 that comes first. Then each column which has a leading 1 has zeros everywhere else. The rest, that's it, just have numbers. And non-zero, or sometimes 0. Now, let's solve this And as I said, when we reduce the system of equations, we change the system, but we do not change the solution. So this has the same solution as that. But what is this? This is in fact this system of equations. Let me write it here. That goes with this system. So I have x1 minus 1 over 7 x3 plus 4 over 7 x4 minus 5 over 7 x5 is 0. And the second one is I have an x2 here minus 3 over 7 x3 plus 5 over 7 x4 minus 8 over 7 x5 is 0. And the last one is in fact 0 equals 0. So the last one doesn't come into the picture. So I had 3 equations in 5 unknowns, and it's reduced to 2 equations in 5 unknowns. Now, how do we solve this? To solve this, we need some free variables. So we have 2 equations in 5 unknowns. We can find 2 of them in terms of the other one. So we need 3 free variables. Now, how do we choose the free variables? Okay, well, these leading ones can be anywhere. So ignore the columns with leading ones. Now let me write on top. So this column is for x1, that's x2, that's x3, that's x4, and x5. So the columns that do not have leading ones, choose them. Choose the variable as free. So x3 should be free, x4 should be free, and x5 should be free. Not these 2, not x1 and x2. So if I let those 3 be free, well, let me give them different name. Let x3 be R, say x4, S, and x5, T. Okay. So these are my parameters given. Well, let me solve it, and then I will tell you what this means. So let me erase this. So if that happens, then first one will be x1 is, let's find x1 in terms of the rest, is 1 over 7 R minus 4 sevenths S plus 5 over 7 and x2 will be 3 over 7 R minus 5 over 7 S and plus 8 over 7. So these are arithmetic equations. In fact, we have to include those 3 here. So let's include these. Well, let's write them in front. So we should include these 3. So we say x3 is R, then x4 is S, and x5 is T. So these are parametric equations, and we call this general solution. General solution. Okay. So general solution is when you find the RREF form, RREF, and then choose free variables and find the other variables in terms of the free variables and write them down as in parametric form. So this parametric form, that is the general solution. Now, what does this mean? It means given different numbers to R, S, and T, we can find x1 and x2. In fact, these are, so you can say this is 1, 1, 1, for example, and find x1 and x2. Say this is negative 2, 5, negative 10, something, and for those 3, you can find x1 and x2. So those are free, but x1 and x2 are not free and they are found, you can calculate them in terms of the free ones. So solving a system of equations is basically doing this RREF. And you will see under the end that most of the things in this in linear algebra that we study are related to this RREF. We can say a lot by finding RREF of a matrix. So this is like central and crucial in studying so many things. Okay, so let me erase this. Now, well, let me give you examples of special cases. So, what if when I do RREF, I will get a matrix like this 1, 0, 0, 0. What is this? Well, it is, in fact, RREF. And if so this has x1 and x2. By looking at this, you just say, I know, x2 should be 3. But let me write it down in the other format. I have nothing else except the first one is telling me that x1 is 0. The second one is just saying that x2 is, in fact, 3. So if I let x2 be t, so x1 is 0 and x2 is t. So the solutions of this system of equations, in fact, are like this. So solutions are things like this. Solutions are this. So let me just sum solutions. So the first one is always 0. So that's 0, say 1. So this is the t. You can have 0 and negative 256. This is the t. And so on. Okay, so in this situation, the first one is not really free. The first one has to be fixed. And the x1 is in fact fixed, and that is equal to 1. It can happen. You will see that this can happen. And so if you see a case like this, don't get confused. It can happen that we might have one of the coordinates or one of the unknowns simply fixed on. Okay, now. So what did we, when the RREF is found, so if given A, find the RREF of A, let's put it in parentheses. So the RREF of A has a special format, that we know the format. Now what can we say by looking at the RREF? So we can say lots of things. So if we have, say, n equations, n unknowns, if unknowns, let's assume that m is bigger than or equal to n. Okay. What if it's not the case? So let me just write some. So if I have x1 plus x2 equals, say, 5, and I have 2x1 minus x2 equals, say, -6, for example. Then I have 3x1 plus 5x2 equals 10, and so on. Even this, I'm not sure that it's consistent. Most often, if I have more equations than unknowns, then the system is not consistent. For example, if I solve these two, well, let me see, if I solve these two, I will get, if I just add them, I will get 3x1 equals -1, so x1 is -1/3, and x2 is something, but you can check, I guess, it's the two x1 and x2 that you find from the two equations, the first two, do not match the third one. So that doesn't have any solution. If you reduce it, you will get like 0 equals some non-zero number. Or I'm not sure. Yeah, I guess yeah, that's true. So then you will get 0 equals the non-zero number. So this kind of system will come up in, say, statistics, for example, in linear regression. You will see systems like this. But for us, usually we have systems where the number of unknowns is bigger than the number of equations. Like the example I gave you, we had 3 equations in 5 unknowns. So the number of unknowns was bigger than the number of equations. When you do the RREF, you might come up with, if RREF of A has R 0 rows, then if it has R 0 rows, then how many free variables do I need? Then we need well, let me see. If we have R 0 rows and we have M, we need at least, well, it's at least n minus m minus n free variables. But if I have more than that, then it's m minus n minus r. Let me see if that is true. So that was the 3 equations and 5 unknowns. 5 minus 3 was 2. Yes. So, and exactly we need exactly n minus n minus minus r free variables. Okay. So the RREF at this point can give us lots of things. One of them is this, and the other one is it solves the equation. Okay, let me see what else is in this section, so maybe I can just go to the next section. Yeah, so since we have a lot of time, I will jump to the next section of this. Still, we are in lecture 2, and I will start. Matrices and matrix operations. So, a matrix A, which we write it like this, Aij, and we write n by n here. So this looks like this. You have some matrices, so this is like something. So the I and j are in fact the index here. So each one of them is called entry. So aij, a ij is the I j entry. Okay. Each one of these is a row, and this one is column. Okay. So for example, this is like second column, and this one is like well, let's write this one. This is the end. So how do you say? So if something is a matrix is given to you by looking at the second index that gives you the column, and the first one gives you the row. So this belongs to aij, belongs to the ith row and the j column. So it's like the intersection of the ith row and the jth column. So the first index is the row, and the second index is the column. Okay. Another thing is this m by n. So this gives me a number of rows, and this one number of columns. And we just say that this matrix has dimension m by n. Or let's say m times n. In fact, we will see why we write m times n, which is like multiplying. In fact, that's correct. That's m times n. So let me put this thing in a set. So let's say we have a set of matrices, and this uses m, and then I can recall which one. Okay, so m, I would say m by n, say, is the set of all matrices like this. Okay. In this set, we can define matrix addition The matrix addition is entry-wise or element-wise. It is element-wise or entry, which means, well, let me with subtraction. Subtraction is in fact the same. And there's another thing. It's called scalar multiplication. This is also element-wise. So everything is element-wise. Let me define each one of them. I mean, I have already defined, but anyway, so let me, or maybe this is not a good definition, but let me write it down more carefully. So, if I have matrix A, which is A11, A12, A1n, A21, A22, A2n, AM1, AM2 to AMN. And I have B, which is B11, B12, k is real number. So we have matrix and scalar, vector and scalar. So scalar is just a real number. So we can say this is like a 1 by 1 matrix. So you can put it in this format, and that's the 1 by 1 matrix. Okay, now adding is element-wise. So a plus b. Let me write here a plus or minus. Plus or minus, that is simply a 1 1 plus minus b 1 1. A 1 2 plus minus b 1 2. A 1 n plus minus b 1 n. Then a 2 1 plus minus b 2 1. A 2 2 plus minus b 2 2. A 2 n plus minus b 2 n. And this goes on to a m1 plus minus a, b m1, up to a mn plus minus b mn. So adding or subtracting is element-wise. That's what I mean, element-wise. So each element is added to its the corresponding element in the other matrix. Now, how do I multiply this a by this k? You can guess. You can guess what happens here. So k times a is simply k a11, k a12, k a1n, k a21, k a2n, and up to k a m1, k a m. So that is scalar multiplication. That was addition and subtraction. Now, this scalar multiplication, I can multiply it by -1. So -1 will give me a negative matrix. So negative a simply is like -1 times a. Negative a is like -1 times a. And that is minus a1, minus a1, up to minus a1n, minus a1, minus a2n, minus a1, minus a. The interesting thing is that a plus minus a is, if I add the element wise, I will get 0 everywhere. So that is in fact 0, 0, 0, 0, 0, 0, 0. So this is the 0 matrix. So if all of them are 0, that is called a 0 matrix. So if A is all zeros, n by n, that is called 0 matrix. Okay. Okay. You might say, so what happens to multiplication? So let me first introduce certain matrices that we will be using. So we have a row matrix, or row vector. So a row matrix is like this. A11, A12, A1. So it is 1 by n. A column matrix column vector is say it's just called B, B11, B21, So that one belongs to M matrices with that dimension, and this one matrices with this dimension. Now, we usually call them row and column vectors, not row and column matrix. But you have to realize that vectors can, when we study vectors, it's like studying matrices, and vectors will be special cases. But having said that, we have something special here when it comes to multiplying matrices. So I should also introduce other matrices here. So square matrix. This one is a square matrix. So square matrix, let me write it here, n by n. That is n by n, a-I-j, n by n. So example, for example, this is square matrix. 4, 5, 6, 7, 8, 9. That's 3 by 3. And diagonal matrix is a square matrix with a ij equal to 0 when I is not equal to j. So like this, B is 1, 0, 0, 0, -2, 0, 0, 0, 23, say. So that is a diagonal matrix. Everything is 0 except entries in the diagonal. So this is called the diagonal. This is the diagonal. And diagonal makes sense when we have a square matrix, right? Diagonal. So if we have a square matrix, we can talk about its diagonal and diagonal terms, and we will see what. Well, these are important. That's why we mentioned them. So now, how do we multiply matrices? So let me. Matrix multiplication. For matrix multiplication, first we define multiplying a row vector by a column vector. So case 1, multiply a row vector by a column vector. So let's say we have A times B, and A is the row vector A11, A12 up to A1n, and B is the column vector B11, B21 up to Bn1. Now you can see the dimension of this, we can say it's n. It's 1 by n, 1 times n is n. The other one is n times 1. But let me define this multiplication, then you will see why I need the same dimension. So A, B, I define it to be a real number, a number. It's a number, or a 1 by 1 matrix, so it is A11, B11 plus A12, B21 plus A13, B31 up to A1 and B and 1. Okay, now you can tell why I needed the same dimension here. Because this is multiplied by the first one, the second one, the third one. So if I have less here, then some of them are left without being multiplied by n. So this should have the same number of terms in a column. So that is A, B. We will see that this is also called the dot product of two vectors. In fact, these two, as I said, these are vectors in different forms, and that's called also called the dot product of two vectors. Now, let me define multiplication of two matrices using this. Okay. Now, when I have a matrix A, Aij, n by n, I can write it in two different ways. One, I can just write it as columns. So this is column number one. Let me put vector notation on top. So this is column number one, column number two, column number three. So how many columns do I have? C2. So this is the number of columns. So it ends at Cn. Okay. I can also write this in row form. Row number one, then row number two, up to row number n. Okay. So I can either write it down as a bunch of columns put together or a bunch of rows put together. Okay, now how do I multiply two matrices? Well, you can guess that I'm multiplying row by column. Because row is a row vector, column is a column vector. So somehow I should turn one of them into this format and the other one into this format and multiply. So what do I need? I need this one and this one have the same dimension. So the dimension of this is in fact the number of columns of the first one. The dimension of this is the number of rows of the second one. So if I want to do this, then I need this. So if this is, say, A, and this is like B, and let me see which one is multiplied by. So let's say this is B, and this is A. And I want to multiply A and B the same way. So I multiply this by this, and this by this by this. I multiply this by each one of them. And if I have to multiply this by each one of them, then this should have the same dimension as this. The dimension of this is, say, n. So if this is m by n, say, so n is dimension of this, then this should be n. So this b should be n times something, r. Right? So the second dimension of this one and the first dimension of this one should be the same. So let me write it again, and in this format, A, n by n can be multiplied by B, n by r. So these two should be the same. And what happens in the end? Well, so this is in fact very simple. This is in fact, it is row I times column j, row I times column j. So this is the Aij or C, let's call it something else. Say Dij. If I say this is equal to D, if this is equal to D, then Dij is an element of this, or an entry of this. Each entry of this is like this. So this should be m by r. M by r. So this middle one just goes away. So let me write this down more loosely. Expanded version of this. So I have R1, C1, R1, C2, R1, C, how many? columns does this one have n? Is it? No. Sorry. This one has the R ones. Then I have R2, C1, R2, C2, R2, CR. Then the last one will be R